and focus on the law of sines. So we're going to work through two of these problems. They're just from the end of the 5.5 notes packet. So our first problem talks about points P and Q that run along a fence and are separated by 140 feet. There's a river in front of the fence and a flagpole located on the other side of the river. Now it turns out that the angle that the flagpole makes with the line segment PQ, just kind of, we can say along with the fence, measures 78.9 degrees from point P to the flagpole. And when we're looking along that fence from point Q across the river to the flagpole, we got an angle of 58 degrees. What are the distances from point P and Q to the flagpole? So here comes our setup. Here's our flagpole. Here's P and Q, which we have said is 140. And I'll go ahead and finish in my triangle, and we'll just draw it to the base of the flagpole. Sorry about my miscue there. We won't worry about the river, but you can pretend, hey, there was the river. We'll get it out of the way just so we can see. I'll go ahead and call this point F for flagpole. I know that little f is equal to 140. Angle F is unknown at the moment, but I know what angle P is, 79 degrees. I know what angle Q is, 58 degrees. Sorry, my 58 got a little bit clipped there. But now I want to find, well, for my triangle, I want to find little p and little q. Let's do some work. Well, what's the nice thing? Well, this is a nice situation where I have two angles and a side. And if you know two angles in a triangle, by default, you can find the third angle. It's going to be 180 minus 79 minus 58, which happens to add up to 137. 180 minus 137 is 43 degrees. What's that help me? Well, now that I know this angle, I can work, because I have all three angles, I can work with a law of sines. So I can say the following. I can say sine of 43 is to 140, as the sine of 79 degrees is to little p, as the sine of 58 degrees is to little q. And so with those setups, I'm going to work with these equations real quick. I can say P equals 140 times the sine of 79 degrees divided by the sine of 43 degrees. And that's going to walk us into a value that's right around 201. I can say that, I'll use these pieces, this and this. I can say that Q is equal to 140, the sine of 58 degrees, divided by the sine of 43 degrees. And I walk through with this, I'll come up with a value of about 174. So P, 201, Q, 174. Do I like these? Well, the answer is, well, I'll trust my numbers for a couple reasons, but one is because the biggest angle has the biggest side opposite. 201 is the biggest of the three. 58 is my smallest, 43 is my smallest angle. And what's my smallest side? 140. Angle Q, 58, is right in the middle of the two, and this is my middle length in terms of, hey, here's the biggest, here's the smallest, here's the one sitting right in the middle. So there's kind of the structure for that first problem. Let's talk about our second problem. And this mirrors some things that you've seen in the textbook with some homework problems that we've had before, just using SOHCAHTOA. It also was a problem that you saw maybe on one of the bonus questions for the test, but we're going to walk through it and let the law of sines help us now. From a point A, the angle of elevation to the top of a tree is 38 degrees. From a point B, 25 feet closer to the tree, the angle of elevation to the top is 48 degrees. How far is point B to the top of the tree? How tall is the tree? So I've drawn, as we've seen before, there's my tree, and I've drawn point A with a 38 degree angle going up to it. I've drawn a point B with a 48 degree angle going up to it. I've identified the fact that the distance from A to B is 25. How can I use the law of sines and other features to help me find X, that's the distance from point B to the top of the tree, and how can I find the height of the tree? Well, a couple ways, lots of ways I can go ahead and do this. I know I have a 90 degree triangle here. 90 plus 48 plus 42 degrees. I already know all the dimensions of this triangle that's sitting here, kind of my tall, skinny triangle. Unfortunately, it's not enough at the moment because I have no lengths. I can't use a law of sines or anything, but maybe if I can solve for x, I'll be back to some of my original days. And let's see if we can do something along those lines. Well, there's a lot of different ways in which we can attack this, but here's probably the simplest way. Notice that these two angles are supplementary angles. They have to add to 180 degrees. That tells me that this is a 132 degree angle. And if I add 132 and 38, this little tiny angle up here is nothing more than 10 degrees. So if I exclusively look at that triangle that I've just kind of highlighted with the squiggles, I can do the following. Hey, I have three angles and I got a side. I can fall back to the law of sines to help me out again. I can say that the sine of 10 degrees over 25 is equal to the sine of 38 degrees over x. And when I do some basic work, I can say x is equal to 25 times the sine of 38 degrees over the sine of 10 degrees. And when I do that, I get a value that's about 88.6. That's what my calculator kicked through. Okay, that's very helpful. So now I know I can work with this second triangle, and let's just go ahead and redraw it real quick. 48, h, height of the tree, and 88.6. So I found the distance from point B to the top of the tree is 88.6. And now, to get the height of the tree, gee whiz, right back to some of my good old SOHCAHTOA stuff. 48 degrees, I'll work with that. I could work with a 42 degree angle up here that we found before, but just work with that. I could say that the sine of 48 degrees is equal to h over 88.6. H, the height of the tree, is nothing more than 88.6 times the sine of 48 degrees. And when I work my way through that, I'm going to get 65.9 feet. That's how tall this tree is. So there are other ways we solved this thing before, but this is a nice concept where the law of sines helps us do what? Well, the law of sines helped us find this length, which serves, by the way, as a hypotenuse of a right triangle. Very, very helpful to get this second piece, and that was kind of the key to the whole problem. Building this squiggly triangle, knowing all the dimensions, law of sines gave us the ability to find this nice little value, x, for this triangle, which in turn becomes the hypotenuse of this other triangle. Away I go, 65.9 as my final solution for the height of the tree. So I hope this helps you out.